Welcome. Today we are looking at rates of reaction at an advanced level. This is a key topic in your chemistry exams for SS3. Pay close attention. Let us begin. First, let me review what the rate of a chemical reaction is. The rate of a chemical reaction is the speed at which reactants are converted into products. It is the change in concentration of a reactant or product per unit time. The rate of a reaction is important in many fields. It determines how quickly a product can be made. It affects the cost of industrial processes. It influences the shelf life of foods and medicines. Understanding reaction rates helps chemists control reactions. They can speed up useful reactions. They can slow down unwanted reactions. The study of reaction rates is called chemical kinetics. Now, let me explain the factors that affect reaction rates in detail. The first factor is concentration. Increasing the concentration of reactants increases the rate of reaction. This is because there are more particles per unit volume. The particles collide more frequently. More collisions lead to more successful reactions. The rate is proportional to the concentration raised to a power. This is the rate law. The second factor is temperature. Increasing the temperature increases the rate of reaction. This is because the particles have more kinetic energy. They move faster. They collide more frequently. They also collide with more energy. More collisions have enough energy to overcome the activation energy. The rate constant increases with temperature. This is described by the Arrhenius equation. The third factor is surface area. Increasing the surface area of a solid reactant increases the rate of reaction. This is because more particles are exposed. There are more sites for collisions. The fourth factor is catalysts. A catalyst is a substance that increases the rate of a reaction without being consumed. It provides an alternative pathway with a lower activation energy. Catalysts are very important in industry. They speed up reactions without being used up. The fifth factor is pressure. For gaseous reactions, increasing pressure increases the rate. This is because the particles are closer together. They collide more frequently. Now let me explain the collision theory in detail. The collision theory explains how reactions occur. It states that for a reaction to occur, particles must collide. They must collide with the correct orientation. The particles must be properly aligned. They must also collide with sufficient energy. The minimum energy required for a reaction to occur is the activation energy. Only collisions with energy equal to or greater than the activation energy result in a reaction. Collisions with less energy do not result in a reaction. They are ineffective collisions. Increasing the temperature increases the number of particles with sufficient energy. Increasing the concentration increases the number of collisions. Increasing the surface area increases the number of collisions. A catalyst lowers the activation energy. This allows more collisions to be successful. The collision theory explains all the factors that affect reaction rates. The collision theory is the foundation of chemical kinetics. Now let me explain the Arrhenius equation. The Arrhenius equation relates the rate constant to temperature. It is K equals A times E to the power of negative EA over RT. A is the frequency factor. It is the number of collisions with the correct orientation. E is the activation energy. R is the gas constant. T is the temperature. The equation shows that the rate constant increases exponentially with temperature. It also shows that reactions with higher activation energies are more sensitive to temperature. The Arrhenius equation can be rearranged to calculate the activation energy. The activation energy can be determined by measuring the rate constant at different temperatures. A graph of ln K versus 1 T gives a straight line. The slope is AR. The activation energy can be calculated from the slope. The Arrhenius equation is important for understanding the temperature dependence of reaction rates. Now let me explain the rate law and order of reaction. The rate law is an equation that relates the rate of a reaction to the concentration of reactants. The rate law has the form rate equals K times concentration of A raised to the power of M times concentration of B raised to the power of N. K is the rate constant. M is the order with respect to A. N is the order with respect to B. The overall order is M plus N. The order of a reaction can be determined experimentally. It is not determined by the stoichiometric coefficients. For example, the reaction between hydrogen and iodine has the rate law. Rate equals K times concentration of H, 2 times concentration of I2. The reaction is first order with respect to hydrogen. It is first order with respect to iodine. The overall order is second order. The rate constant K depends on temperature. It increases with increasing temperature. Now, let me explain the methods for determining the rate law. There are two main methods. The initial rate method measures the rate at the beginning of the reaction. The concentration of reactants is varied. The initial rate is measured for each concentration. The order with respect to each reactant is determined by comparing the rates. The integrated rate law method uses the integrated form of the rate law. The concentration is plotted against time. The order is determined by which plot gives a straight line. For a first-order reaction, a plot of Ln concentration versus time is linear. For a second-order reaction, a plot of 1 divided by concentration versus time is linear. The integrated rate law method is used to determine the order of a reaction and the rate constant. The half-life of a reaction is the time required for the concentration of a reactant to decrease by half. For a first-order reaction, the half-life is independent of concentration. For a second-order reaction, the half-life is inversely proportional to concentration. Now, let me explain the mechanisms of reactions. A reaction mechanism is a series of steps that lead to the overall reaction. Each step is called an elementary step. The elementary steps involve the collision of molecules. The slowest step is the rate-determining step. The rate law is determined by the rate-determining step. For example, the reaction between nitrogen dioxide and carbon monoxide has a proposed mechanism. The first step is 2NO2 equals NO3 plus NO. The second step is NO3 plus CO equals NO2 plus CO2. The overall reaction is NO2 plus CO equals NO plus CO2. The first step is the rate-determining step. The rate law is rate equals K times concentration of NO2 squared. The rate law is consistent with the mechanism. Reaction mechanisms are important for understanding how reactions occur. They help explain the rate law and the effect of catalysts. Now, let me explain the effect of temperature on reaction rates. Increasing the temperature increases the rate of reaction. The rate constant increases with temperature. The Arrhenius equation describes this relationship. The activation energy also affects the rate. Reactions with high activation energies are more sensitive to temperature. They increase more with temperature. Reactions with low activation energies are less sensitive to temperature. They increase less with temperature. The rule of thumb is that the rate doubles for every 10 degrees Celsius increase in temperature. This is true for many reactions near room temperature. However, it is not exact. The exact relationship is given by the Arrhenius equation. Now, let me explain the effect of catalysts on reaction rates. A catalyst increases the rate of a reaction by lowering the activation energy. It provides an alternative pathway. The catalyst is not consumed. It can be used again. Catalysts are specific to particular reactions. They work by forming intermediate compounds. The intermediate compounds then decompose to give the products and regenerate the catalyst. Catalysts are used in many industrial processes. The Haber process uses an iron catalyst. The contact process uses a vanadium pentoxide catalyst. The catalytic converter in cars uses platinum and rhodium. Enzymes are catalysts in biological systems. They are very specific. They work under mild conditions. They are essential for life. A common exam question asks you to explain the factors affecting reaction rates. Here is a sample answer. The factors affecting reaction rates are concentration, temperature, surface area, catalysts, and pressure for gases. Increasing concentration increases the rate. Increasing temperature increases the rate. Increasing surface area increases the rate. Adding a catalyst increases the rate. Increasing pressure increases the rate for gaseous reactions. These factors affect the number of collisions and the energy of collisions. The collision theory explains these effects. Another exam question asks you to explain the Arrhenius equation. Here is your answer. The Arrhenius equation relates the rate constant to temperature. It is K equals A times e to the power of negative EA over RT. A is the frequency factor. Ea is the activation energy. R is the gas constant. T is the temperature. The equation shows that the rate constant increases exponentially with temperature. It also shows that reactions with higher activation energies are more sensitive to temperature. The activation energy can be calculated from the Arrhenius equation. Another exam question asks you to determine the rate law from experimental data. Here is your answer. The rate law is determined by the initial rate method or the integrated rate law method. The initial rate method measures the rate at the beginning of the reaction. The concentration of reactants is varied. The order with respect to each reactant is determined by comparing the rates. The integrated rate law method uses the integrated form of the rate law. The order is determined by which plot gives a straight line. The rate law is rate equals K times concentration of A raised to the power of M times concentration of B raised to the power of N. Let me give you a quick summary. The rate of a reaction is the speed at which reactants become products. Factors affecting rate include concentration, temperature, surface area, catalysts, and pressure. The collision theory explains reaction rates. Activation energy is the minimum energy for a reaction. The Arrhenius equation relates rate constant to temperature. The rate law relates rate to concentration. The order of a reaction is determined experimentally. Reaction mechanisms explain the steps of a reaction. Practice these concepts. When you have them down, move to topic 5.